Every hour, over 10,000 engines are started worldwide. But what if I told you that behind their operation lies one of the most spectacular, secretive, and precise procedures on the planet? Before you is a huge red-hot cylinder, as long as a bus and weighing as much as a small tank. It will go through the hell of presses, a ritual of grinding down to the micro-inch, and even immersion in boiling oil. This is the story of the creation of a supertanker's heart, a giant crankshaft capable of pushing 400,000 tons through the ocean. But there's one detail that isn't shown in any documentary film. Watch until the end, and you'll find out what exactly makes metal live. For such wonder parts, high-strength alloy steels are used, often with additions of chromium, molybdenum, or vanadium. They provide resistance to fatigue loads and corrosion. The steel must meet strict standards. Its chemical composition, purity, and grain size are checked. This is the heart of the future engine, so there can be no mistakes here. Crankshafts for the most powerful diesel engines are usually forged, not cast as one might think. The reason is a denser metal structure and the absence of voids or cracks. The blank is first heated in a forging furnace to 2,300 degrees Fahrenheit. Then, it is gradually shaped by giant presses that exert a force of over 50,000 PSI. A huge steel cylinder, glowing orange-red as long as a bus, weighing under 60,000 pounds. It has just been taken out of the furnace. A wave of hot air emanates from it, forcing workers to keep their distance. The floor underfoot vibrates. The forging begins. This is not a hammer and anvil. This is a hydraulic press as tall as a 2-story building, which, with pressure, slowly and confidently squeezes the perfect shape of the future crankshaft out of the metal. The red-hot block is placed under the press, and with a dull thud, it compresses the steel, changing its structure. Inside, the crystalline lattice melts, becoming denser, stronger, more resistant to future loads. This is just the first strike, then another, and another. Huge manipulator jaws turn the blank at the right angle. It is stretched, bent, compressed, all to form the basic geometry of the shaft: journals, cheeks, counterweights. After several deformations, it is sent back to the furnace. Metal doesn't like to be rushed. If it cools, it becomes brittle. If it overheats, it loses its properties. Nearby, an operator watches every movement through protective glass. Every millimeter matters. A half-inch error can cost thousands of dollars and weeks of rework. On the screen, a temperature map of the part, the press pressure, the feed angle. After just a few cycles, the blank begins to resemble something familiar. It is still far from the finish line, but the shape gradually emerges, a huge skeleton of the future mechanism that will turn the shaft at a speed of 80 revolutions per minute and push the supertanker forward. The supertanker is an incredible 437 yards long. That's almost 4 football fields. After the final strike, the part is slowly pulled aside onto a cooling platform. Steam rises above it, and the crackling of the contracting metal can be heard. Mechanical processing still lies ahead, but already this is a crankshaft blank, the heart of an engine that will feel every wave of the ocean. After all these manipulations, a blank that has been through the hell of forging stands in the workshop, a red-hot steel bone, over 33 feet long, weighing under 25 tons. It already resembles a crankshaft, but only resembles. The surface is all in rough marks from the press. The edges are uneven, and the tolerances are far from precise. And here begins the finest, slowest part: machining. The giant part is carefully installed on a lathe the size of a bowling alley. It is clamped in jaws that can withstand pressures of thousands of PSI, and rotation is started. And slowly, carefully, a cutting tool approaches the surface. The metal is turned layer by layer, no more than 0.02 inches at a time, and each of these layers is machined with surgical precision. The lathe is connected to a computer numerical control system, and it forgives no mistakes. Here, thousandths of an inch decide everything, because if the engine's rhythm is uneven, the ship won't be able to hold its course. After rough turning, they move on to milling, forming lubrication holes, making grooves, grinding bearing seats. The tools are coated with diamond dust or made of hard carbide, otherwise they simply wouldn't withstand contact with such dense steel. During processing, the shaft rotates slowly, just 2 or 3 revolutions per minute, sometimes even slower. It is lubricated with a special cooling lubricant, because without it, the tools would overheat and microcracks would appear on the surface. Each surface is checked after a pass with dial indicators and a laser measurement system. No more than 1/1000th of an inch of error. That's the tolerance for the journals that contact the bearings. Everything must be perfectly round, perfectly smooth, perfectly weighted. The crankshaft is a rotating system, and the slightest imbalance in such masses will cause vibration that will tear the engine apart from the inside. Therefore, it is placed on a special stand, sped up, and with the help of high-precision equipment, it is determined where exactly an extra 5 or 6 ounces of steel need to be removed so that the weight is distributed perfectly. After this, final grinding is required. Grinding heads are used to polish the journal surfaces to a shine. Now its dimensions can be measured not in inches, but in micro-inches, because every microscopic defect means overheating, friction, wear. Everything is recorded in a quality certificate, and if something doesn't comply, the blank is sent back to the furnace. This stage takes from several days to several weeks, depending on the shaft's size. But in the end, the output is a perfect steel giant that will rotate in the depths of the engine with a force capable of pushing hundreds of thousands of tons forward. After the crankshaft surface is polished to a shine, a mysterious, almost alchemical stage begins: heat treatment. At first glance, it's already finished, but inside, the metal is not yet what it should be. It needs to be hardened, literally and metaphorically. Because this shaft will work in hell, under loads of tens of thousands of pounds, at temperatures over 300 degrees Fahrenheit, for thousands of hours without rest. The crankshaft is placed in a huge thermal furnace. This is a steel chamber the size of a truck. The temperature gradually rises to 1,500 degrees Fahrenheit, and so the shaft bakes for several hours, sometimes up to a day. This is structure normalization. Upon heating, the steel grains expand, and the stresses that accumulated after forging and machining disappear. The internal metal becomes homogeneous, more elastic, ready for loads. After heating, the part must be hardened. The shaft is taken out and quickly cooled. This can be an oil bath, hot oil in which the steel hisses and bubbles as if boiling, or a controlled flow of air from nozzles. It all depends on the type of steel. But the essence is the same. With rapid cooling, the outer layer becomes super hard, forming a so-called hardened crust capable of resisting wear and friction. But such hardness has a side effect: brittleness. So next, tempering. The shaft is heated again, already to 1,000 degrees Fahrenheit or slightly less, and held for several hours. This restores its balance. The metal remains hard, but no longer brittle, like a well-tensioned spring. Strong, but elastic. At the end, induction hardening for the most critical zones, the necks and seating areas. They are treated with high-frequency currents. A contour coil surrounds a part of the shaft, creating local heating, followed by instantaneous cooling. This allows strengthening only those areas that receive the greatest loads, without affecting other parts. After the heat treatment is complete, the crankshaft falls into the hands of quality control specialists, and here begins the final, most important act in the creation of this giant part. Not only the engine's operation, but also the safety of the entire vessel depends on the accuracy and reliability of these checks. The first step is a visual inspection. Specialists carefully check the shaft's surface for cracks, scratches, defects in painting or coating. For this, they use magnifying glasses and special lighting devices capable of detecting even the smallest irregularities. After all, any microcrack can become a point of failure during operation. Then, ultrasonic scanners are used, which penetrate deep into the metal and detect internal defects, voids, inclusions, stresses in the structure. The crankshaft is wrapped with special sensors, and a computer system reads the signals and creates a 3D map of its internal structure. Next, magnetic particle inspection. This method allows finding the smallest surface cracks that may be invisible to the naked eye. The crankshaft surface is coated with a magnetic powder, and under the influence of a magnetic field, the powder particles gather at the defect sites, clearly highlighting them. Every single year, more than 200,000 hydrocycles are sold all around the globe, and the overall market for this type of equipment exceeds $2.5 billion United States of America dollars. But how does a piece of composite material turn into a genuine water monster that can accelerate up to 70 miles per hour? What makes the Japanese Yamaha factory the largest hydrocycle manufacturer in the entire world? From automated hull molding to the most advanced engines and on-water testing, today we are going to unveil every secret of their production. Fasten your seatbelts, because we are heading into a realm of high speeds and groundbreaking innovations. The design of hydrocycles begins with conceptual ideas and essential requirements for technical specifications. The very first stage involves identifying the target audience and the purpose of the hydrocycle. It can be a recreational model, a sports or extreme hydrocycle, or even specialized versions for fishing or rescue operations. Designers and engineers must consider not only the visual appeal, but also factors such as maneuverability, stability, top speed, comfort, and water safety. They carefully think through each detail so that the final product meets the needs of both beginners and seasoned riders. According to Statista, the global hydrocycle market by the year 2027 will grow to over $2.5 billion United States of America dollars, with an annual growth rate of 8.3%. This impressive forecast shows just how much interest hydrocycles continue to generate in different parts of the world, especially as new technology makes them more efficient, eco-friendly, and fun to ride. One of the biggest markets for hydrocycles is the United States of America, where more than half of all hydrocycles worldwide are sold. This country remains a leader in water sports development, partly because of its numerous resorts, lakes, rivers, and coastlines, which make hydrocycles immensely popular among both local residents and tourists. Hydrocycles are also well liked in Australia and Japan, where water activities are an integral part of cultural traditions, and people love to explore different forms of aquatic adventure. During the development stage, important factors include the design of the hull, which must be light yet strong and resistant to mechanical damage. For this purpose, high-quality materials such as fiberglass, composites, and aluminum are used to achieve the required rigidity without adding too much weight to the hydrocycle. Another critical consideration is the choice of engine. Most hydrocycles use internal combustion engines, although a growing number of manufacturers are experimenting with electric models, which offer cleaner emissions and produce less noise. In modern hydrocycle design, special attention is paid to innovative technologies, including digital control systems, integration of the global positioning system, and sensors for monitoring the condition of the equipment and improving navigation. These features not only make the experience more convenient for the rider, but they also boost overall safety through automatic stability control systems or engine rotation alerts. All of this simplifies the hydrocycle piloting process and makes it safer, even for first-time enthusiasts. The United States of America holds over 50% of the global hydrocycle market. Another notable trend is the rising demand for electric hydrocycles. Although they currently occupy only a small share of the market, their environmental advantages could make them a key part of the hydrocycle industry's future, since they help reduce emissions and lower noise pollution levels on the water. An essential element of design involves creating an ergonomic layout that ensures comfort during lengthy rides or races. Seats must be comfortable and provide proper support for the rider's posture, while also featuring a non-slip surface that holds up in wet conditions. Additionally, hydrocycles are equipped with various features, such as extra storage compartments, waterproof pouches, and cooling systems that help the vehicle operate at high revolutions over long periods. Developing new models also requires numerous water tests to check how the hydrocycle performs in real conditions. This process helps identify any weaknesses in the design or technical parameters, which are then corrected before the start of mass production, guaranteeing that customers receive a high-quality product. The hydrocycle development process is extremely detailed and demands meticulous attention at every phase, from designing the hull to testing the final product. Engineers, designers, and manufacturing specialists must work in close collaboration to produce equipment that is not just powerful and fast, but also safe and comfortable for users. Hydrocycles need to be easy to maneuver on the water, while also having enough durability to withstand heavy loads, water pressure, salt, ultraviolet radiation, and other environmental factors. These stringent requirements mean that the choice of materials for different hydrocycle components must be carefully evaluated to balance weight, strength, and resistance to corrosive elements. First and foremost, a key element of any hydrocycle's construction is its hull. This is one of the main parts that must be strong enough to resist mechanical damage and, at the same time, provide optimal hydrodynamic characteristics. The most common materials for hull manufacturing include fiberglass, composite substances, and aluminum. Fiberglass is selected because it offers high strength at a low weight and is resistant to corrosion, making it ideal for use in aquatic environments. In addition, it can be molded easily, allowing engineers to create sleek, aerodynamic shapes for the hydrocycle hull. Composite materials, which include polymers reinforced with fibers such as carbon or Kevlar, are even more advanced, delivering greater strength while reducing weight. They also exhibit excellent resistance to ultraviolet exposure and chemical agents like salty water solutions. By combining these materials, manufacturers can cut down on hydrocycle weight while improving speed and maneuverability, which is especially beneficial for sports-oriented models. When it comes to internal components, such as fuel tanks and cooling systems, manufacturers often rely on stainless steel or specialized plastic blends. Stainless steel is a long-lasting material that resists corrosion, making it perfect for repeated contact with water and various liquids. Plastic blends, such as high-density polyethylene, are used due to their lightness, durability against chemical and mechanical impact, and ability to function effectively for extended periods in high humidity conditions. Another crucial consideration is the choice of materials for hydrocycle engines. Lightweight yet powerful substances are essential for achieving high revolutions without sacrificing endurance. Typically, engine components are made from metal alloys, including aluminum, titanium alloys, or magnesium. These materials have low density, which helps reduce engine weight, and they have excellent thermal conductivity, which is critical for efficient cooling and overall engine performance. One well-known hydrocycle manufacturing facility is located in Japan, operated by Yamaha Motor Company, which is widely recognized as one of the leading brands in the watercraft market. Situated in the city of Iwata in Shizuoka Prefecture, this factory produces not only hydrocycles, but also other types of water transport and their engines. The Yamaha Motor Factory spans approximately 250 acres, making it one of the largest facilities in the world dedicated to water equipment production, including hydrocycles. The site specializes in manufacturing a broad range of water transport products, including diverse hydrocycle models, boats, yachts, and other motorized water vehicles. Every year, this factory turns out thousands of products, including over 60,000 hydrocycles annually, which secures Yamaha a substantial market share in the water transport sector. Thanks to the factory's expansive premises, every stage of production, from assembly to testing and packaging, can be carried out efficiently and in one location. One of the main automated lines is responsible for forming hydrocycle hulls using materials such as fiberglass and composites. This line is equipped with robotic arms that precisely shape and join individual hull components, delivering the exact design contours and a smooth exterior finish. In addition, automated welding and painting systems are used to process metal parts, such as engines and their subsystems. The line features robotic welding machines that provide accurate, high-quality welds, as well as automated painting systems that evenly coat components and offer reliable protection against corrosion. This advanced technology helps ensure the product maintains a pristine appearance and robust structure over an extended service life. The assembly lines have a real-time quality control system, which automatically identifies defects at any stage of production. This includes visual inspections using cameras and scanners capable of detecting even the smallest flaws in parts, allowing the factory to preserve the highest possible product quality. A distinctive feature of this factory is its extensive automation in the packaging and shipping phases. Once hydrocycles have passed all quality checks, they move on to automated packaging lines, where robotized systems assemble boxes and secure the hydrocycles inside transport containers. This process enhances shipping safety and streamlines logistics, ensuring that the products are delivered to customers in excellent condition and on schedule. The Yamaha factory continuously adopts the latest technologies in water equipment production. For instance, they use three-dimensional printing to create prototypes of new models, enabling faster testing and refinement of their designs. Moreover, the facility employs pioneering materials that help reduce the weight of hydrocycles, increase their corrosion resistance, and extend their service life. They also make active use of intelligent production management systems, which optimize manufacturing processes, cut down on costs, and shorten the time needed to produce each unit. As a result, the factory can expedite hydrocycle manufacturing and boost output volume, illustrating Yamaha's commitment to continuous innovation and leadership in the fast-paced world of hydrocycle development. Imagine a machine that can withstand the blast of a high-explosive device, endure fire from automatic weapons, and keep rolling even with shot-through tires. This is the legendary Hummer, designed for the most dangerous missions. From operations in the Persian Gulf to modern combat zones, over 280,000 armored Hummer vehicles have become an essential part of the United States Army. How do these machines go through their testing? Which materials protect the crew? And why do they produce 70 of them per day? Let us find out. To understand why the Hummer became synonymous with invincibility, one should first look back at its history. In the 1980s, the American automobile company called AM General unveiled a modified Hummer that was initially developed for the civilian market. However, the troops quickly recognized its advantages for modern warfare, especially on the front lines, where soldier protection is paramount and armored vehicles became critically important for safety. A true breakthrough came after the Hummer became the main transport vehicle for the United States military during operations in the Persian Gulf at the beginning of the 1990s. Since the year 1893, over 280,000 Hummer units have been manufactured. But how can one ensure that this off-roader not only endures harsh conditions, but also provides protection in the most hazardous situations? What exactly sets the military armored Hummer apart from civilian models? Let us see how the armored components are constructed to turn these vehicles into a genuine steel shield on wheels. Military Hummer vehicles use specialized armor materials, including composite armor that combines steel plates with ceramic inserts. These materials can withstand shots from a variety of weapons, including automatic rifles and sniper rifles. Moreover, by incorporating composites, these vehicles are not only armored, but also relatively light for their size. The production rate is around 70 vehicles per day. A key structural element of the armored Hummer is the concept of plus armor. This means that multiple layers of protection are added onto the vehicle, enabling maximum defense in a wide range of combat scenarios. There are also additional design modifications, such as reinforced suspension and strengthened tires, allowing the vehicle to keep moving even if one of the tires has been damaged. Another important aspect is the strengthened floor and roof. In military Hummer vehicles, the floor is structurally protected against blasts. Special materials are used to absorb the shockwave, which reduces risk to the crew if the vehicle encounters a minefield or an explosive device. However, armor is only one part of the overall safety level. Each high-mobility multi-purpose wheeled vehicle, commonly known as the Hummer, consists of over 5,000 parts. Combat Hummer vehicles must not only be protected, they must also be real beasts capable of moving through absolutely any conditions. How is this kind of mobility achieved? In order to preserve high off-road capability and endurance, military Hummer models are equipped with a powerful diesel engine. This engine can generate substantial power that lets the vehicle easily travel through desert sands or mountainous routes, even if there is no road at all. A specialized transmission and adapted rear wheels ensure constant stability in the most extreme conditions. Many modern military Hummer vehicles integrate intelligent control systems that allow the engine and transmission to adapt to the terrain. This significantly boosts maneuverability and endurance during large-scale strategic movements. Armored versions receive steel that is 1/2 inch thick, along with bullet-resistant glass that is 1.5 inches thick. Besides armor, electronic safety systems are vital, such as sensors that detect mines and explosive devices, along with systems designed to remain fire-resistant. They add another layer of protection for the crew, which is particularly critical in combat situations. What else is worth mentioning when talking about armored Hummer vehicles? There are several technical considerations to bear in mind. Military Hummer versions often feature specialized camouflage coatings that help them blend into the environment. This is crucial for enhancing survivability on the battlefield, where every detail can make a difference. Interestingly, the Hummer is not a static vehicle. Its design allows modifications based on mission needs. These can include additional weapon systems, medical equipment, or other specialized modules, depending on the task at hand. A military Hummer can carry up to 2,500 pounds of cargo or tow up to 7,500 pounds. Producing armored Hummer vehicles is a complex and lengthy process that demands highly skilled engineers and advanced technology. Everything starts with meticulous planning. Engineers account for every aspect, from improved mechanical components to resilience during blasts. Multiple prototypes are built, each undergoing a battery of tests. They are dropped from heights, fired upon, and examined for endurance in different conditions. Previously, AM General, the company that originally created the legendary Humvee, was in charge of production. However, in the year 2020, the license to manufacture new military vehicles was granted to Oshkosh Defense. As a result, combat Hummer vehicles are gradually being replaced by the Joint Light Tactical Vehicle, a more modern armored off-road vehicle. Therefore, military and civilian versions are produced separately, using different factories, technologies, and even materials. The body and armored panels are cut using laser or plasma machines, and then they are welded by robots and highly qualified specialists. Precision is crucial, because all seams must be airtight to enhance blast resistance. The Hummer is built on a robust steel frame, designed to withstand high loads. The chassis and engine are assembled separately, then tested for functionality. Only after that are they joined with the body. Once the main parts are put together, the vehicle is fitted with armored panels and additional protection. This stage is time-consuming because every component must be installed with the utmost precision. The interior of a military Hummer is nothing like that of a civilian vehicle. Everything is dedicated to functionality. Some models have air conditioning, which is essential in desert conditions. After assembly, the vehicle is painted with special scratch and corrosion-resistant paints. Several options are employed: desert camouflage for sandy regions, woodland or urban camouflage for the respective environments, and anti-radar coating to reduce visibility on radar systems. This is no ordinary paint. It is formulated to withstand heat, freezing temperatures, and the impact of blasts. The high-mobility multi-purpose wheeled vehicle is not produced in the same way as mass-market civilian cars. It is manufactured in relatively small batches, so fully automated production is impractical. At the same time, certain processes, such as welding and painting, are streamlined by a conveyor system for speed and consistency. Each high-mobility multi-purpose wheeled vehicle is equipped with a 396 cubic inch diesel engine that outputs 190 horsepower. This powerful diesel engine is engineered to operate under extreme conditions. The transmission is a 4-speed automatic adapted for off-road use. The vehicle has permanent four-wheel drive and automatic differential locks. It accelerates to 37 miles per hour in approximately 17 seconds. It is slow, but speed is not the main goal for the military. For military transport, the priorities are off-road performance, reliability, and endurance. The high-mobility multi-purpose wheeled vehicle is not designed for swift maneuvers, but for traveling over any type of terrain. It has a high ground clearance of 16 inches, which allows it to clear rocks, ditches, and logs. Full-time four-wheel drive and differential locks prevent it from getting stuck in mud or sand. The engine and fuel system are protected to withstand fire and blasts. There is minimal onboard electronics, meaning fewer things can break down in the field. It can continue moving on punctured tires. Special inserts allow driving even after the tire has been hit by a bullet. Its payload capacity allows transporting ammunition, injured personnel, and weapons ranging from machine guns to anti-missile systems. It may not be the fastest ride, but it will get you where others simply cannot go. The standard military high-mobility multi-purpose wheeled vehicle initially did not have armor, but since the year 2000, most models have received protection against small arms fire and shrapnel. Configurations vary, from soft body transport versions to the most widespread ones, capable of withstanding a high explosive device blast of up to 13 pounds. There are models with protection systems against chemical, biological, and nuclear weapons. Assembling a single high-mobility multi-purpose wheeled vehicle takes from 3 to 5 days, depending on the armor. At the AM General facility, where they build the high-mobility multi-purpose wheeled vehicle, there can be up to 3,000 workers in one workshop. However, only about 25 or 30 individuals work on assembling a specific vehicle at any given time. These include welders, mechanics, electricians, and armor specialists, each carrying out their tasks at each stage of the production line. The more complex the version, the more time and personnel are required. Before they are shipped, all high-mobility multi-purpose wheeled vehicles undergo 310 miles of test trials across off-road terrain, water, and dust. You already know how the Hummer is painted, but allow me to elaborate on the special matte paint known as chemical agent-resistant coating, which has several important properties. It does not reflect infrared light, making it harder to detect the vehicle with thermal imaging and night vision equipment. It resists chemical attacks. Its formulation makes it easier to wash off hazardous substances following chemical contamination. It withstands scratches and corrosion, enduring impacts from branches, sand, rain, sun, and aggressive liquids. The matte finish eliminates glare, which is critical for battlefield camouflage. The painting process involves multiple layers that are applied to the aluminum body and armored panels. Every single year, the world's oceans are left with hundreds of gigantic liners that used to be floating cities. Imagine this. Only one specialized shipyard in the country of India dismantles over 400 ships per year, and the utilization of just one cruise liner can yield up to about 44,000 short tons of steel. How does a vessel that once cost billions of dollars turn into a heap of scrap metal? Who makes money on this process? And why do the majority of ships finish their journey in Southern Asia? Let us examine this process from the very first blueprint all the way to the very last cutting of the hull. Private yachts are produced all over the world, including in the United Kingdom, the Netherlands, Italy, and Turkey. But the major cruise liner production hubs are located in France, Germany, Italy, and Finland, where industry giants such as Chantier de l'Atlantique, Meyer Werft, and Fincantieri operate. Everything begins with the creation of a project, during which engineers and designers develop the overall structure, choose materials, and determine the technical specifications of the vessel. The design phase can last anywhere from 6 months to 5 years. Once it is approved, the shipyard begins manufacturing the main metal sections of the hull, which are later joined together in a massive dry dock or a specialized construction hangar. Construction starts with the production of large steel or aluminum sections that will form the hull. First, enormous sheets of metal are cut using laser or plasma cutting, and then they are joined by welding to create separate blocks. Each block can weigh anywhere from about 55 short tons to about 330 short tons. and their total number may reach into the hundreds, depending on the ship's size. After the welding is completed, the sections are painted with anti-corrosion coating and moved into a massive assembly dock, where the hull begins to take shape. The assembly process involves powerful cranes that lift the blocks and connect them to one another. Once the main structure is finished, the hull is reinforced with internal bulkheads, and initial communications are installed, including piping systems, ventilation ducts, and electrical cables. When the hull is fully assembled, it is launched into the water, and the fitting out of the interior begins. Partitions, electrical grids, heating and ventilation systems, air conditioning, and safety systems are put in place. At this stage, the ship gradually starts to look the way it will when it is completed. First, special soundproofing and thermal insulation materials are applied to the ship's metal hull, because the liner must be not only strong, but also comfortable. Next, metal frameworks are installed to serve as the foundation for the partitions and other structures. These frames are made of lightweight materials, such as aluminum or composite panels, to keep the vessel's overall weight lower. Thanks to modular technology, large sections of cabins and public areas are assembled at separate production facilities and then transported to the liner, where they are rapidly installed. Passenger cabins are usually manufactured as complete blocks, each including walls, flooring, plumbing, and furniture. These blocks are then transported to the ship and placed in their designated spots, after which they are connected to the ship's electrical network and water supply and ventilation systems. Larger liners can have more than 2,000 of these modules, and installing them can take several months. Public areas are much more complex, since each restaurant, theater, or lobby has its own design and intricate architectural solutions. For example, theater stages are equipped with moving platforms, sound systems, and lighting that is integrated into the ceiling. Swimming pools receive water purification systems, and sports courts are fitted with special non-slip surfaces designed to withstand wave movement. During the final stage, furniture, decorative panels, lighting, and finishing touches are installed. High-quality materials are used, ranging from exotic woods and marble to stained glass. Designers pay attention to every single detail in order to create an atmosphere of luxury and comfort. Once construction is complete, all systems undergo meticulous testing, including elevators, ventilation, safety features, and communication lines, so that the liner is fully prepared to welcome passengers. At the same time, powerful engines and control systems are installed on board. The main engines, which are typically diesel or hybrid, are mounted in the engine room before the liner's hull is completely enclosed. Each engine can weigh anywhere from about 22 short tons to about 55 short tons, and there may be between 3 and 6 engines depending on the ship's size. They are delivered to the shipyard dock by specialized cranes, then lowered through the engine room's top hatch and attached to vibration-damping mounts that reduce noise and vibration during operation. After the engines have been installed, drive shafts are added to transmit rotational motion to the propellers, or, in the case of electric motors, they are connected to the power supply system. Most modern liners use azipod units, which are powerful electric motors capable of rotating around their own axis, giving the ship excellent maneuverability. All power units are connected to control systems located on the bridge and in the engine room. Once every technical system is in place, the liner is readied for its initial tests. First, static tests are conducted while the ship is still in the dock, checking how the engines function without leaving port. The power units are started up, and the electrical supply, fuel pumps, cooling systems, and emergency mechanisms are tested. Computerized control systems, which manage navigation, automatic speed adjustment, and ship stability, are also checked at this stage. Following these static tests, the liner is launched for sea trials, which last from about 2 weeks to about 6 weeks and include checking speed, maneuverability, and the operation of all systems under real-world conditions. The captain and technical personnel test how the vessel responds to commands, examining braking efficiency and the performance of the stabilization systems. The liner is taken into open waters, where the engines are tested at maximum power. Fuel consumption is measured, and noise and vibration levels in cabins and public areas are evaluated. In the final phase of testing, safety systems are examined by simulating emergency scenarios, testing firefighting systems, lifeboats, evacuation routes, and communication with shore-based services. Only after all tests are successfully completed is the liner formally handed over to the client, and it sets sail on its maiden voyage. But sooner or later, every liner heads out on its last voyage. Since no technology lasts forever, what happens to yachts and other vessels afterward? Are they actually utilized? And if so, how? According to data from the International Maritime Organization, around 1,000 seagoing vessels are utilized each year, of which about 200 are large cruise liners and passenger ships. Most of these vessels are dismantled in South Asian countries such as India, Bangladesh, and Pakistan, where the world's largest ship utilization shipyards are located. For instance, in the city of Alang in India, there is one of the biggest shipyards, which processes over 400 ships per year. First, the ship's owner assesses the condition of the liner and compiles a list of materials that can be recycled, sold, or require specialized disposal. The utilization of a single large cruise liner can produce up to about 44,000 short tons of steel, which, after recycling, is used in construction and other industries. In addition to metals, other materials such as wood, glass, and plastic are removed from the vessels for recycling or safe disposal. During this period, the ship heads to the specialized shipyard that handles the disassembly of ships. The largest of these facilities are located in India, Bangladesh, Turkey, and Pakistan. The liner or yacht makes its way to the site for utilization under its own power, or is towed if its engines are no longer functional. When the vessel arrives at the shipyard, the preparatory work begins. A team of engineers and environmental specialists evaluates the potential risks connected to hazardous substances, including fuel, lubricants, coolants, chemicals, asbestos, and lead. All of these materials must be carefully removed to prevent environmental contamination and to protect the workers' safety. In the first step, any remaining diesel fuel is pumped out of the tanks, which can amount to anywhere between about 10 short tons and about 55 short tons, depending on the size of the vessel. Next, the pipelines, oil filters, and engine cooling systems are cleaned to remove all residual lubricants and chemicals. Specialists also deal with air conditioning and firefighting systems, which might contain harmful gases like freon. After that, the ship is disconnected from all power. The electrical networks are shut down, and the batteries containing toxic substances are removed. In the engine room, the generators are dismantled. They can be resold or used on other ships. During this period, specialists also check for hazardous materials, such as asbestos, which was once used for pipe and wall insulation. Asbestos is carefully taken out, sealed, and delivered to specialized facilities for safe disposal. The next step involves removing all equipment and items that might be reused or sold. Furniture, lighting fixtures, plumbing, doors, decorative panels, carpets, and even kitchen appliances are dismantled from the liner. Many of these items are sold on the secondary market or used on other vessels and in hotels. The following stage is dismantling. First, the ship is secured in a dry dock or pulled onto a specially designated beach, which is common in South Asian countries such as India or Bangladesh. This stabilization is necessary to keep the hull steady during cutting because losing balance could cause an accident. Next, the upper structures are gradually taken apart, including the top decks, bridge, funnels, and other external components. These sections are typically removed in large pieces using cranes. Workers start dismantling the upper structures and decks, steadily moving down toward the main hull. Metal parts like steel and aluminum are cut into smaller segments, and the separated materials are sorted and prepared for subsequent recycling. For example, steel is melted down to create new products, while non-ferrous metals such as copper and aluminum are put to use in various industries. When the upper structures have been fully removed, the main hull is cut apart. Several methods can be used, depending on the thickness of the steel and where the ship is located. The most widespread method is gas cutting, where specialized torches heat the metal to over 1,500 degrees Celsius, which is about 2,732 degrees Fahrenheit, and then the steel is sliced by a stream of oxygen. For thicker steel sections, which can be up to about 8 inches thick, plasma cutting or hydraulic shears may be used. Cutting of the hull begins from the top and proceeds downward, so that the structure does not collapse under its own weight. huge steel blocks, weighing anywhere from about 55 short tons to about 110 short tons, are separated and moved to specialized areas, where they are further broken down for recycling. On average, the hull of one large cruise liner can yield from about 33,000 short tons to about 44,000 short tons of steel, which is later reused in construction and shipbuilding. Special attention is paid to cutting the underwater part of the hull, since it is the sturdiest section and contains ballast tanks that might hold residual water. Underwater welding and cutting techniques are employed if part of the hull remains in the water at that stage. In the final phase of dismantling, the last remains of the keel and bottom are cut into fragments, which are loaded onto trucks or barges for transport to metallurgical plants. Utilization of cruise liners and yachts can last from a few months to more than 1 year, depending on the vessel's size and construction. Completing the dismantling process signifies that the ship officially ceases to exist. All materials suitable for reuse are sent for recycling, and everything else that cannot be repurposed is disposed of in accordance with environmental regulations. It is important to note that the utilization process must meet international environmental standards. Organizations such as the International Maritime Organization develop guidelines and standards for the environmentally sound utilization of ships, known as the Hong Kong International Convention for the Safe and Environmentally Sound Recycling of Ships. Every single day, more than 20 million banknotes are destroyed in the United States. That is a mountain of money that could reach the sky. But what exactly happens to them? Are they burned, shredded, or maybe turned into something completely unexpected? US dollars have their own life cycle, and their disposal is a high-security operation involving armored trucks, strict inspections, and secret routes. How do old banknotes disappear forever? And is there any way to save them? Let's find out. The dollar as a currency has a fascinating history. It all began in the mid-17th century. The first dollars appeared in the New England colonies in the year 1690, at a time when the United States did not yet have a unified national currency. Back then, the colonies issued their own money, and one of these was the so-called paper dollar. However, the true dollar as we know it today emerged later, in the year 1792, when the United States Congress passed the Coinage Act. This was the country's first attempt to introduce a single currency, establishing the dollar standard based on a silver coin. The dollar quickly became the main currency for trade and wealth accumulation, as the nation sought to create a stable and accessible monetary system that would support its economy and commercial ties. Today, the dollar has evolved into one of the world's leading currencies, used in international transactions across the globe. The idea of disposing of old banknotes arose at the beginning of modern financial systems, especially when currencies started to become standardized and central banks began managing the money supply. In other words, the process of removing worn-out dollars started as soon as money became a stable and regulated instrument, though it was not officially systematized until much later. The concept of destroying damaged money first appeared in Great Britain during the 19th century, when the British government realized that allowing worn-out banknotes or coins to remain in circulation reduced the overall value of the currency. However, the systematic destruction of money, as it is done today, only became possible with advancements in modern financial systems and technology. In the United States, the first efforts to manage old and worn-out dollars began in the mid-19th century, when the first central authorities responsible for currency emerged, and money became a key instrument of the national economy. In the year 1861, when the United States first introduced federal paper money, known as greenbacks, the need arose to organize their circulation, including their disposal. The official process of destroying old dollars was established by the Federal Reserve after its creation in the year 1913. The Federal Reserve became the primary institution responsible for regulating the money supply, including removing old banknotes from circulation. The idea of destroying old banknotes was first introduced by central banks, which discovered that worn-out and damaged money not only harmed the image of a national currency, but could also create economic problems. If old banknotes remained in circulation, it could destabilize the monetary system, increase the risk of counterfeiting, and even affect inflation rates. To prevent this, the Federal Reserve established a clear policy outlining when and how banknotes should be removed from circulation. This became an essential part of maintaining economic stability. So, what exactly happens to all the money that can no longer be used and that no one wants to see anymore? Are they just burned? Well, not exactly. Disposing of US dollars is a complex process that follows a highly regulated system, ensuring both destruction and security. Here's how it works. First of all, when money is removed from circulation, whether it is declared damaged or obsolete, it does not simply get thrown in the trash. Everything goes through the United States Federal Reserve System, which manages the issuance and renewal of dollars. They collect old banknotes and send them to specialized facilities for further disposal. When you or someone else brings damaged or worn-out dollars to a bank, that is where the process begins. Banks have strict procedures for identifying banknotes that are no longer fit for circulation. These banknotes are inspected both manually and automatically using specialized machines that detect damage, wear, or counterfeit signs. Modern ATMs and cash dispensers are also equipped with sensors to detect worn-out banknotes. If a bill is found to be damaged or degraded, it is usually placed into special compartments or sent to sorting machines in banks. Once a sufficient number of old banknotes accumulate in banks, they are sent to the next stage, the Federal Reserve. These are special facilities located across the country that inspect, replace, and dispose of currency. Several such centers exist across the United States, strategically positioned to efficiently serve all regions. The process of transporting old banknotes to the Federal Reserve or specialized disposal facilities is strictly regulated. Banks typically work with security firms specializing in transporting large sums of money. Old banknotes are packed into special bags or containers that are sealed and secured against unauthorized access. This is crucial because even old money remains a potential target for theft or counterfeiting if not handled properly. Security guards or specialized couriers deliver these packages to the Federal Reserve or disposal facilities. The transport companies involved in this process operate under the highest security standards, and shipments are often escorted by police or other security services when necessary. You would not believe how many old banknotes accumulate each year, and this applies not only to US dollars, but also to other currencies. Bank vaults are not limitless in space, so from time to time, large batches of worn-out bills must be removed. Every day, thousands of banknotes pass through people's hands. Some get crumpled, some get coffee spilled on them, and some even end up in the laundry. Add the natural wear and tear, and you have a massive pile of money that is no longer usable. Imagine this: every single day, the United States Federal Reserve destroys millions of banknotes. If you stacked them up, they would reach as high as a skyscraper. And that is just in one day. Transporting such massive amounts requires trucks. Money is packed into special bags or boxes. Each container has a unique number and seal to ensure it remains unopened. And while these may no longer be real money in a traditional sense, they still hold value. So the security of such shipments is incredibly tight. It is almost like a scene from an action movie. Armored trucks, armed guards, secret routes. Except here, instead of a heist, the mission is to get rid of this money forever. A true financial thriller, right? Before the old banknotes are destroyed, they go through careful inspection. Special systems determine whether they can be reused. If a banknote still retains at least 50% of its original form, it can be reintroduced into circulation after a special treatment, such as reprocessing or trimming. This significantly reduces the cost of printing new banknotes. Every year, an enormous amount of old dollars is destroyed in the United States. For example, in the year 2020, around 7 billion banknotes were eliminated because they were too worn out to remain in circulation. This process is continuously maintained at the highest level to keep the currency stable. Some damaged banknotes are not immediately burned. Instead, they are recycled into other materials, such as fibers that are later used to produce new banknotes. This helps reduce production costs and support sustainability efforts. There is also an interesting psychological aspect to this process. For many people, destroying money might seem like a loss of value, but in reality, it is part of a continuous cycle that helps preserve the stability and worth of the currency. That is why this process is just as crucial as printing new money. Old US dollars are often destroyed in specialized incinerators or through processes that ensure maximum material utilization. Banknotes are burned at temperatures of approximately 2,000 degrees Fahrenheit, completely obliterating them. Furthermore, advanced filtration and technology capture toxic gases and other harmful byproducts to ensure safety during the process. But does it not feel strange to burn so much money? Given how much we spend daily, these sums seem enormous. However, the portion of money that gets destroyed is actually a tiny fraction of the total circulating supply. In the end, the system is highly reliable and efficient. After the banknotes are burned, tons of ash remain. Some companies repurpose this ash into materials for making compost or even bricks. This part fascinates me. Dollars get reborn and continue serving humanity in new ways. Every single day, at the Lockheed Martin factory in Fort Worth, Texas, fighter jets roll off the production line, ready to dominate the skies. This is where the legendary F-16 Fighting Falcon is assembled, each one a true engineering marvel. In just 52 days, hundreds of specialists, robotic systems, and thousands of components come together to create a combat machine capable of reaching speeds of 1,500 miles per hour. How is this steel predator built? I visited the factory and saw it all with my own eyes. Ready to dive into the heart of aircraft manufacturing? Buckle up, we are taking off. At the massive Lockheed Martin factory in Fort Worth, Texas, the day begins with the roar of machinery. Gets the adrenaline pumping, right? My heart is racing. Here, in the heart of aerospace engineering, one of the most famous fighter jets in the world, the F-16 Fighting Falcon, is brought to life. But the process of building each F-16 begins long before the first part arrives at the factory. Engineers at Lockheed Martin start by working with 3D modeling systems using CATIA V5 and Siemens NX software. A digital twin of the aircraft is created to test virtual aerodynamics, simulate material strength, and optimize the placement of cables, pipelines, and electronic systems. After that, supercomputers run numerous simulations to predict how the F-16 will perform at different speeds, in combat maneuvers, or under extreme temperatures. To test the strength of the structure, prototypes of key components, such as the wings, nose section, and tail, are built and subjected to rigorous lab tests. They undergo vibration-resistant simulations to mimic turbulence, as well as extreme temperature exposure, heating up to 302 degrees and cooling down to minus 76 degrees Fahrenheit. And let's not forget impact resistance tests, like simulating a bird strike at 559 miles per hour. You love crash tests too, right? It is thrilling. Meanwhile, a separate team works on the cockpit. Test pilots evaluate the ergonomics of the instruments, the positioning of the HUD display, and the ease of control. As for the materials, supply issues are never a concern. Lockheed Martin signs contracts 2 to 3 years in advance. The standard material set includes aluminum and titanium alloys from Alcoa and Timet, which form the fuselage structure, composite materials from Toray and Hexil, used for wings, fairings, and radar-absorbing elements. Aerospace electronic systems, including radars, avionics, and targeting systems, are provided by Northrop Grumman and Raytheon. In the morning, the factory floor at Lockheed Martin has a quiet but focused atmosphere. This is not just manufacturing. This is where fighter jets that will rule the skies are born. Workers are at their stations. Some are prepping riveting guns. Others are reviewing blueprints, while some are operating laser measuring systems. Today, another F-16 Fighting Falcon is being assembled, and everything must be flawless. As you might have guessed, the factory follows a modular approach. Instead of building an entire jet in one place, it is assembled in sections before being joined together. In one of the workshops, the aluminum cockpit frame is already complete. Nearby tables hold avionics instruments, HUD displays, and computer system modules. Workers in white gloves carefully install them into compartments. The ejection seat mount is fitted, and a 12mm thick bulletproof canopy glass is installed, capable of withstanding a 13mm bullet impact. 12.5 miles of wiring are laid out, connecting sensors, displays, and control systems. Meanwhile, the central fuselage section is being assembled, the area that houses the fuel tanks, landing gear, and wing mounting points. A large aluminum frame is secured with 40,000 rivets installed by automated riveting robots. Fuel tanks with a total capacity of 845 gallons are integrated into the structure. The landing gear, capable of handling loads up to 44,000 pounds, is installed and tested. Workers meticulously check the tanks for leaks by filling them with a special gas and inspecting for any seepage. In the adjacent workshop, the tail section takes shape. It is welded together using titanium and composite panels, with an engine mount already in place, designed to withstand temperatures exceeding 2,192 degrees Fahrenheit. The elevator and rudder are then installed, followed by a check on the emergency braking mechanism. A specialized team handles this section since the tail not only controls flight, but also maintains the jet's overall balance. The wings are assembled in a dedicated section. Hydraulic mechanisms for controlling flaps and ailerons are installed, along with hardpoints for weapons. The composite wing surfaces undergo ultrasonic testing for defects. If even one layer of carbon fiber is improperly placed, the wing could deform under combat stress. So there is zero tolerance for errors. Once all modules pass rigorous inspections, they are transported to the final assembly line. The final assembly line is a massive hangar stretching 437 yards long, where hundreds of specialists work in precise coordination. Everything follows a strict schedule. Any delay in one step can impact the entire process. The central fuselage is lifted by a specialized crane and aligned using lasers. First, the cockpit is attached, followed by the tail section. Engineers use high-strength titanium bolts capable of withstanding loads of approximately 88,180 pounds. Once the primary structure is complete, it is time to attach the wings, which are secured with reinforced titanium joints to ensure structural rigidity. Engineers meticulously check the alignment angles to ensure the error margin does not exceed allowable limits. After assembling the airframe, one of the most critical moments arrives: the installation of the jet engine. It is transported in a specialized container and lifted into the tail section using a hydraulic hoist. Technicians carefully connect all systems: fuel lines, hydraulic and electrical cables, and the afterburner system that enables supersonic flight. Once installed, a dry test run is conducted to verify its operation without fuel ignition. The onboard computer, pilot displays, weapons control systems, and the ANAPG-83 radar, capable of detecting targets at a range of 100 miles, are then integrated. Before the first flight, the F-16 receives anti-corrosion treatment, paint, and stealth coating. As a kid, my best friend was obsessed with origami. She was into everything from Eastern culture, so origami never stood a chance of being ignored. Me? I was terrible at it. My fine motor skills were not exactly top-notch, so while she was crafting intricate dragons and delicate flowers, I was busy making paper planes of all sizes and launching them from my window into the backyard. Could I have imagined back then that I would one day step into the legendary Lockheed Martin factory and witness the birth of an F-16 with my own eyes? Absolutely not. Before an F-16 takes to the skies, it must undergo a series of ground tests. Every flight system, electronics, fuel supply, and hydraulics is tested on the ground first. The engine is warmed up to operational temperature, and the exhaust system and airflow temperature in the ducts are inspected. Special attention is given to the ACES-2 ejection seat and emergency systems that might be needed in a crisis. Once all ground systems pass, the pilot receives clearance for the first flight. Communication with ground controllers and engineers is checked in real time. The jet slowly rolls toward the runway, then accelerates to around 3,000 yards per hour for an optimal takeoff. After liftoff, the landing gear retracts smoothly. Everything is functioning perfectly. At an altitude of around 3,300 yards, the pilot executes the first maneuvers, testing aerodynamics, elevator, aileron, and flap responses at different speeds. The F-16 is then pushed past Mach 1 to test the afterburner system. This phase measures aerodynamic stress, identifying any defects at high speeds. G-force tests follow, as the pilot executes precise maneuvers to ensure stability under varying attack angles and velocities. After completing initial flight tests, the pilot begins the descent. At 3,000 yards, the landing gear deploys, and the pilot prepares for touchdown. The effectiveness of brakes and the auto-stabilization system is evaluated. The moment the F-16 touches the ground, it decelerates quickly. Engineers conduct final inspections of electronics, fuel systems, and structural integrity. Data is then analyzed, and if everything checks out, the F-16 is officially cleared for duty.